All right, this is the Newton's third law video. So Newton's third law of motion is also known as the law of action and reaction. So for every action, there's an opposite and equal reaction. So there are the five key components to Newton's third law of motion is that forces always occur in pairs. Force pairs are always equal in magnitude. Force pairs are always oppositely directed. Force pairs always occur simultaneously, and force pairs never cancel because they act on two different bodies or two different objects. So let's answer this question. Which football player is hitting the other one harder? So we know that each player, because of Newton's third law, exerts the same force on each other. Now, we know the same player applied the force at the exact same time. Both players applied that force at the exact same time. They applied the force for the same amount of time because force pairs are simultaneous. Now, they don't cancel out because they're acting on two different objects. One of the forces acting on player A, the other force is acting on player B. Now, you can already look at this photo and say, well, that force just has a larger effect on player A. So these forces are going to be opposite and equal. All right, now let's look at a bug hitting a windshield. So we know that the force of magnitude. So which object, the bug or the windshield, if either exerts a larger force of magnitude to the other object, we know that they are going to be equal. We know that they are going to be simultaneous. So they are applied at the exact same time for the same amount of time, and they don't cancel because they're acting on two different objects. One of the forces acting on the windshield, one of them is acting on the bug. Now we know, like just from experience, that the force is going to have a larger effect on that bug because the mass is so much smaller. So these forces are going to be equal, but the effect is not going to be equal. So we did this lab. It's the Don't Nickel and Dime Me lab. So essentially, if you're sliding a nickel and a penny together, we know that they at the moment of collision that those forces are going to be opposite and equal, and they're going to be applied for at the same time for the exact same amount of time. Now, if you did this experiment, it's gonna have a larger effect on that penny. That penny is gonna go bouncing off, but the nickel will just sort of come to a rest. And the reason is because the mass, the resistance to that force of that penny is going to be lower than the resistance to the force of that nickel. So we know that the penny is going to have a larger acceleration because the ratio of that net force to mass is going to be a lot larger. So these are the free body diagrams of what happens during that collision. And so if this experiment were to be conducted again with a quarter instead of a nickel, well, the quarter, it would have less of an effect on the quarter because the quarter has more inertia. So it's going to resist that change in motion more. Now, if they were conducted with the same coins, well, the effect would be the same because they have the same resistance to that force, the same inertia. Now, so explain why the penny and the nickel accelerated the way that they did during the collision. So essentially, what it is that, well, you have the same force that's being applied to both of these objects, but because the penny has less inertia, less resistance to that force, it's going to accelerate more. All right, so now let's ask this question and answer it. How do rockets work in the vacuum of space where there's nothing to push off of? So to answer that, we need to look at the Hero's engine. So if we look at the Hero's engine and you pour water into the Hero's engine, it's going to spin. Now you fill it up even more, and the water amount, and it's going to spin more times. So while the Hero's engine is spinning, which object, water or the Hero's engine, if either, exerts a larger force and magnitude to the other object? Explain your answer using Newton's third law. Use the phrase force pair. So what's happening is that the water is pushing on the straw, or the straw is pushing the water out. The water is pushing right back on the straw. Those forces are going to be equal in magnitude. Now, they're applied at the exact same time. They're simultaneous. Force pairs always occur simultaneous. And they occurred for the same amount of time because force pairs are simultaneous. So this is what those diagrams are going to look like. Now notice, if you just look at what's in red, that's what's being applied to the Hero's engine. The green is what's being applied to the water by the Hero's engine. So you'll notice that that top one, well, you have like a torque motion because you have, it's going to be applying the water is going to be applying the force on the straws, and that torquing motion is going to spin it. But if you bent the straws out, straight, well, those forces would sort of push in and they would balance each other out. So the okay, so essentially what happens is the more water you put into it, the more the longer the force was applied to the hero's engine, and it would spin more. So it spins because of Newton's third law, because as the straw pushes that water out, the water pushes right back on the hero's engine. So the last question is sort of the crux of the whole thing. Cars accelerate by using the friction of the ground. Airplanes fly by pushing off the air in Earth's atmosphere. Space is a vacuum, which means there's nothing to push off of. Use Newton's third law. Explain how rockets work when there's nothing to push off in space. So let's look at that. So if we look at that cars, well, what's happening is that the tires are pushing on the ground. There's that static frictional force. So that means the ground, that static friction is pushing right back on those tires, and that force is what's going to accelerate that car forward. Well, planes, what they do is the engine pushes on the air, and the air action reaction pushes right back on the plane. I'm going to have that net force, so the plane is going to accelerate. Now, rockets are a little bit different. What happens is there's nothing to push off in space. There's no friction, there's no air, there's nothing to push off of. So what they do is rockets have to bring what they push off of in space. So that's why rockets are so big. They have to bring that reaction mass. So what happens is it superheats that gas and it pushes it out the end. So if the rocket is pushing on that gas, the gas is pushing right back on that rocket. So now let's answer this question. What determines the winner of a game of tug of war? So if we look at these teams, A and B, which team applies a larger force and magnitude to the other team? It's going to be the same because the force pairs are going to be equal. So which team applied that force first? They happen simultaneous. They applied it for the same amount of time because those force pairs are simultaneous. Now, if the force pairs are equal and opposite, why don't they cancel out? Well, because they act on different objects. One of the forces is acting on team A, the other force is acting on team B. So let's answer this question. How does a team win a game of tug of war? And to give you a hint here, what is applying a force in the outward direction? Would it help or hurt the team if they were standing on ice during the match? So what I want you to see here is that, okay, A is pulling on B, B is pulling on A. These are going to be opposite and equal. But if I put team A on a block of ice and team B on like a rubber mat and they started pulling, well, team B is going to have more traction. Yeah, they're pulling with the same force, but team B can apply a larger force in the outward direction in order to win the game of tug of war. So you don't win necessarily by being the stronger team. You win by having the most traction and able to apply that frictional force outward more than the other team. So let's answer this question. How much does the earth weigh? So if you're looking at a scale, well, it's essentially weight is the force of gravity. So you don't really ask how much does the earth weigh. That doesn't really make much sense. Because if you look at a person on a scale, well, which object has a larger mass? Well, it's going to be the earth. Which object, if any, exerts a larger force and gravitational force and magnitude to the other object? Well, the earth is pulling on this person. The person is going to pull right back on the earth with the same force. So they both apply these forces at the same time, simultaneous, for the same amount of time. Now, so what I want you to see is that the earth is pulling on the person is pulling right back on the earth. But the effect of gravity is much larger on the person because they have such a smaller mass. So let's answer this question. This might help clear some things up. Can you move the earth by using nothing more than a penny? So let's look at that concept of weight and gravitational pull. So if you drop a penny, the the object, the earth or the penny, if either exerts a larger force and magnitude to the other object, they're going to be the same. They applied the force simultaneous, so at the exact same time. They applied the force for the same time, simultaneous. They are opposite and equal, but they don't cancel out because they act on two different objects. One of the forces acting on the penny, one of the other forces acting on the earth. Which object, the earth or the penny, does that force have a larger effect on? Well, obviously, it's going to have a larger effect on that penny. And it's because, well, it has a smaller mass. Look at the mass of the earth. So, and the mass of the penny is so much smaller. So the earth is pulling on the penny's pulling right back on the earth. Well, so the net force as the penny's falling, well, yeah, so that means it's going to accelerate. There's that same force acting on the earth. Now, however, if we look at the ratio of net force to mass, well, the acceleration is going to be a lot larger because I have a large net force divided by, a very small mass. I'm going to have a large ratio, a large acceleration. But now let's look at the ratio. So it's the same net force, but a much, 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 much larger uh, mass resistance to that force. So I'm going to have such a small acceleration. So yes, when you drop a penny, technically the Earth is going to move up towards it just slightly. And yeah, because it's acting on one side more than the other, it's going to be more of a stretching effect. But yeah, dropping a penny does have an effect on the Earth because of Newton's third law. So these are just some final thoughts. Remember, there is too much unknown in the universe to take a break from learning. Get out there and question everything.